OpenTelemetry has become the de facto standard for instrumenting applications. Developers add OTel SDKs to their code and emit spans, metrics and logs, describing exactly what the application is doing at runtime. The question is, where does that data go? Most monitoring platforms treat OTel as an export destination. They push data out to OTel collectors. A platform that acts as an OTLP receiver flips that relationship, and the operational difference is significant. The OTLP protocol, OpenTelemetry protocol, supports both gRPC and HTTP transport. An OTLP receiver listens for instrumented application data and ingests it directly. This happens without a separate collector pipeline. When synthetic checks and OTel spans live in the same system, the relationship between user experience and internal code becomes visible. It becomes a single query, not a manual correlation across two separate tools. This direct ingestion is the foundation of structural observability. OpenTelemetry unifies three signal types that historically required separate pipelines. Traces tell the story of a single request from entry to completion. Which services handled it, how long each took, where errors occurred. Metrics aggregate that story into trends, request rates, error percentages, and latency distributions. Logs capture the structured event narrative, what the application decided, and why. A platform that ingests all three can answer questions about causation, not just correlation. The practical power of synthetic plus OTel together is diagnostic precision. Imagine a synthetic check detects a 503 error at 1422. The OTel trace for that same request shows a database span that took 8.4 seconds. That's 28 times its normal latency. The synthetic check found the outage. The OTel trace found the cause. That two-signal workflow is only possible when both live on the same platform with perfectly aligned timestamps. One important consideration: OTel traces generate high cardinality data. A high-traffic service may generate millions of spans per hour. Look for a platform that supports head-based or tail-based sampling at the ingestion layer, not just at the SDK, so you can capture every error trace. By sampling successful requests and keeping 100% of errors, you control storage costs without losing any diagnostic coverage for when things go wrong. One of the most operationally useful OTel patterns is span-level latency budget analysis. A user-facing request has a total latency SLA, say 300 milliseconds. That budget must be distributed across authentication, application logic, and database queries. OTel traces make that distribution visible. You can see that 210 of those 300 milliseconds are spent in one database query, and that latency has been trending upward for 10 days. That's a capacity planning signal. The evaluation question: does the platform accept OTLP as an ingestion source, or does it only export to OTLP-compatible backends? If the answer is export only, you need two systems, one for synthetic and one for traces. And every cross-signal question requires data federation. If the answer is ingestion, synthetic and OTel data share timestamps, asset context, and alert routing from day one. Ingestion versus export. The direction matters.